Alright, so we will be now starting with Maris, presenting about nuclear fusion. Let's all give a nice little warm applause. I'm kind of obsessed with applause at this point. Yeah.
Hello, my name is Bucur, and I'm here to talk about nuclear fusion as a possible solution to the energy crisis. So the world today is facing an energy crisis. The rise in population and urbanization will scientists predict that this will cause demand of energy to triple by the end of the century. And with the energy sources that we're using now, you will not be able to sustain our lifestyles with this growing demand. The most popular energy source is our fossil fuels, but they are really not optimal. First of all, fossil fuels emit greenhouse gases, which are very harmful and toxic for climate change and every plant, animal, and human on this planet. But they are also not a renewable energy source. So at the rate at which we are exhausting fossil fuels, we will run out of them very, very soon. And if something isn't done quickly, we will not have the infrastructure ready to switch from fossil fuels to another energy source quickly. So that time, before we run out of fossil fuels, there will be economic chaos before we can switch to another energy source. Therefore, scientists have begun looking for alternative energy sources that are clean, efficient, and relatively cheap. Two of the best alternatives are solar power and wind power, but they both have their own drawbacks which hinder them from becoming a mainstream energy source. Firstly, they are both very reliant on changing weather. So large corporations will be very reluctant to invest a lot of money into an energy source that is so reliant on an external factor which they cannot control. They will probably opt out to use more reliable fossil fuels. Secondly, they are not as efficient or as cheap as fossil fuels. For the same amount of investment put into it, the same amount of space, and the same amount of power, they will not produce as much energy as fossil fuels. And there's also no efficient way to store solar or wind energy that cannot be used immediately. The most efficient way to store them is batteries, which aside from being a generally inefficient way to store energy, is also batteries need to be replaced quite constantly. And the inside of the batteries is made of lithium and other toxins, which when disposed of are extremely harmful to the environment. And lastly, they both require vast amounts of space, which some cities and countries simply do not have. Another alternative is nuclear fission, which is taking a larger element and splitting it into two smaller elements to gain energy. But nuclear fusion, although it is efficient, does not require a lot of space, and is relatively cheap, has its own major drawbacks. There is always the possibility of a nuclear meltdown, which of course is one of the most catastrophic things that could happen to human civilization and should be avoided at all costs. But even if in the lifetime of a nuclear power plant reactor there is no nuclear meltdown, there will for sure be nuclear waste, which needs to be disposed of very deeply underground so it does not harm its surrounding environment. And even if it is disposed of perfectly, some radioactivity will seep out and damage its surrounding environment. Therefore, scientists have begun looking for another energy source, an energy source that can power the whole world cleanly and efficiently and cheaply. The source of energy that powers our sun and every other star in the universe, nuclear fusion. Nuclear fusion is taking two lighter elements, putting them under immense heat and pressure, and making a heavier element, releasing energy in the process. In a star, nuclear fusion occurs at its core, and its core is extremely hot and dense because the star is such a massive celestial body. But to achieve the same conditions to fuse on Earth is extremely difficult. One of the best ways to achieve nuclear fusion on Earth, one of the most efficient ways, is using a tokamak reactor, which is basically a nuclear fusion reactor in the shape of sort of a donut, as can be seen here. And basically what happens is hydrogen gas is put inside of the reactor, and it's heated up until it becomes a plasma. That plasma, filled with hydrogen gas, will be heated and heated until the hydrogen gas inside of it begins to fuse. And the fusion causes energy which the tokamak reactor will capture and turn into electricity. So what happens inside of the reactor during the fusion reaction? So basically, the best fuel to fuse is hydrogen gas of two different isotopes, deuterium and tritium. The deuterium and tritium gas is placed inside of the reactor and heated up until it becomes a plasma. In plasma state, the deuterium and tritium gas is naturally stripped of its electrons, so it creates a pool of randomly moving positively charged ions. These ions naturally repel each other, so they do not fuse. But as the plasma continues to heat, at a point around 150 million degrees, this natural repulsion is overcome, and the tritium and deuterium begin to fuse and create helium, releasing energy and a neutron in the process. But how is energy actually gained from this reaction? Well, if the tritium and deuterium are examined closely, it can be seen that they are actually significantly heavier than the resulting helium atom after a fusion reaction. But in any chemical reaction, matter cannot be destroyed or created, so all mass must be somehow conserved. So what can account for this missing mass, known as a mass defect? Well, this can be answered using Einstein's Equation E equals mc squared, which states that energy is equal to mass times light speed squared. Light speed being a constant, and the energy and mass being on different sides of the equation, we can infer that energy and mass are actually interchangeable. So the missing mass that we are seeing is not actually missing mass, but it's mass converted into energy during the reaction, which is lost into heat, which is what the tokamak reactor captures and turns into electricity. But to reach 150 million degrees in order to fuse tritium and deuterium, a lot of machinery and a lot of high efficient power needs to be put into it. And scientists have yet to get more energy out of a fusion reaction than it takes to actually get the elements to fuse. Yes. So a tokamak reactor uses 3 heating methods. The first is electric induction, and there are 2 other external heating methods. One of these is natural beam ejection, where a non-charged, high-energy particle is shot at the plasma to speed up collisions. To speed up collisions, yes, and therefore heat up the plasma. The second is the same concept used to heat up food in a microwave, high-frequency wave transfer. This is where high-frequency waves are passed through the plasma, with the wavelength matching that of the plasma, and the energy of the waves is transferred to the particles of the plasma, causing them to speed up and therefore heat up. And although this seems like straightforward technology, it still requires massive amounts of power to actually get these machines to work. And although humans have yet to achieve net energy gain, it is very possible that this will be done by 2035. There's currently an international project underway whose goal is to build a demonstrative tokamak reactor that can produce tenfold energy gain. So for every 10 megawatts put in to power the reactor, 100 megawatts are given out by the reactor. This is the construction site of the project in France, and it is actually the most expensive and one of the most ambitious scientific projects on Earth, costing just over $22 billion. So governments and scientists are putting a lot of money and a lot of effort to develop nuclear fusion. But is it worth all the hassle? Well, firstly, nuclear fusion is an extremely efficient energy source. At its peak, scientists predict that for the same mass of fuel, it will be able to create 4 times as much power as nuclear energy, and 4 million times more power than burning coal or oil. Secondly, it emits no greenhouse gases, so it is not harmful to the environment and does not contribute to climate change. The main byproduct of a fusion reaction is helium, which is an inert, non-toxic gas that can release into the atmosphere in any abundance and not cause any sort of harm. And unlike in a nuclear fission reaction, there is no possibility of a nuclear meltdown. If anything goes wrong inside of the reactor, no matter how major, the plasma will simply cool and expand, causing no harm to any humans. The only harm can possibly be done is to the reactor itself. It also produces no nuclear waste. Unlike the nuclear fission, the only part that becomes radioactive is the inside machinery of the tokamak reactor. But that can be reused many times for many years. And when it does need to be replaced, it is only slightly radioactive and can be reused safely after 100 years, as opposed to the tens of thousands of years it takes for nuclear fission material to wear off its radioactivity. And lastly, it is basically a renewable energy source. The fuel necessary to power a fusion reactor is deuterium and tritium. And deuterium can be found in abundance in seawater and can be easily extracted. There is enough to power the whole world to last humans millions and millions of years. Tritium, however, is a little bit more difficult because it is radioactive in nature and there's only 24 kilograms of it found naturally. However, a tokamak reactor can actually produce its own tritium fuel. Tritium can be artificially made when a high energy neutron collides with lithium, and the two react and create tritium and helium. Therefore, the walls of a tokamak reactor are lined with lithium blanket modules. It's basically just a blanket filled with lithium. So in every fusion reaction, when a neutron is expelled, that neutron collides with a lithium blanket, collides with the lithium inside of that blanket, creates tritium, which is absorbed and used in later reactions. So basically, a tokamak reactor has its own self-sufficient source of tritium. And there is enough lithium to create these blankets to last humans around 6 million years. Nuclear fusion is an extremely promising energy source, but there are still unanswered questions. Could it become commercially profitable? Is it realistic that we will have it by the end of the century? Scientists cannot answer these questions, but with the vast amounts of money and effort put in by corporations, scientists, and governments, it is clear that nuclear fusion has sheer massive potential. And if humans manage to develop it to its full potential, it will undoubtedly be one of the greatest scientific discoveries. Thank you.